So, time travel. It's impossible, right? It leads to all sorts of paradoxes. Well, maybe not. According to the latest research, time travel may actually be possible. Prepare for your brains to be fried. Over the next 30 minutes, I'm going to take you on a whistle-stop tour of the very latest thinking about time travel. And I'll meet scientists working at theory's cutting edge with ideas which will blow your mind.
Asymmetry between past and future breaks down, and so many strange things can happen.
It's not true anymore that there is a definite past and a definite future.
But let's start right at the beginning. Welcome to the grandfather paradox. This is the main reason we all think that time travel has to be nonsense. But imagine I have a time machine and I travel back, say, 75 years into the past. You find your grandfather, presumably a young man, then you kill him. So he fails to meet your grandmother, and so your mother is never born, and so you never existed. But if you never existed, who went back in time to kill your grandfather? To be honest, this scenario has always bothered me a bit, and not for the obvious reasons. It's complicated. Why skip a generation? Why not just go back and kill your mother? Much cleaner. Actually, that's worse. But maybe there is an even simpler version, which is in fact much more revealing. A scientist finds an instruction manual for building a time machine on his desk. So he decides to study it. And over the next 10 years, builds his own time machine. It's only then that he realizes how the instruction manual arrived in his possession. He starts the time machine and travels 10 years back to the past, to the night before he first discovered the manual. Puts the manual back on his desk for his younger self to find. And then uses the time machine and travels forward to his own time once more. Then, once again, a scientist finds the instruction manual for a time machine. For me, this is much richer as a story because it opens up not one, but 5 clear paradoxes. Paradox number 1, the free will paradox. The scientist has to take the instruction manual back in time because that's how he found it in the first place, in order to build the time machine. What if he decides not to take it back? It's as though he has no free will in the matter. If we live in a deterministic universe, it's one thing to say that the future is determined by the past. But here, it's as though the past is determined by the future. Paradox number 2, the bootstrap paradox, as in being pulled up by its own bootstraps. The time machine manual never seems to have been created. He found it on his desk, he used it to build a time machine, and then travel back in time to put the manual on the desk. It's caught in a logically consistent time loop going round and round, but at no point was it ever created. How did those atoms of ink arrange themselves on the pages of the manual? It doesn't seem to have any moment of creation at all, but just exists, caught in an endless loop. Number 3, the mass energy violation paradox. The scientist goes back in time and leaves the manual, and then, let's say, goes back to his own time. But there was a certain period when there were 2 of him in the universe. So there's more mass. This violates one of the sacred laws of physics, the fact that mass energy of the universe has to be conserved, has to be constant. Where did this extra mass come from? Well, it was borrowed from the future. In fact, it could be even worse. What if he goes back into the past and decides to hang around and help his younger self build the time machine? Then, 10 years later, they both get in the time machine and travel back, and they meet their younger selves. So now there's 4 of them who could all go forward in time and all 4 go back. And you're sort of doubling up the mass of the scientists every time with every loop. Paradox number 4 is the rewriting the past paradox. There can only be one version of history. So the time traveler going back in time can only change things and make them turn out the way he remembers them. So, for example, if he doesn't remember meeting his older time-traveling self when he was young, then there must be a way of forbidding him from ever meeting up with his younger self. And that just doesn't make sense. And now for the final paradox. In a way, this is the most disturbing. Let's call it the infinite time accumulation paradox. You see, it's all very well for the time traveler to take the manual back, leave it on the desk, and then go back to his own time in the future. But think about the manual by itself. It's being used for 10 years to build a time machine, whereby it's taken back in time, and another 10 years go by where it's used again and again in an infinite loop. And in any chosen cycle, the time machine manual will be infinitely old and nothing but a pile of dust, which is no good to anyone.
3, 2, 1, top, décollage.
These paradoxes seem convincing, undoubtedly. But for me as a scientist, the key is what the physics actually says. Let's first consider time travel to the future. In a very real sense, Einstein's special theory of relativity allows this. You see, relativity theory allows for the possibility of slowing time down. This is called time dilation. And it can be done in 2 ways. I can either travel close to the speed of light, so that someone observing me fly past will see my time literally running slower, my clock's ticking slower, or I can find myself a strong gravitational field, because gravity also slows time down. So I can imagine traveling off into the galaxy at close to light speed, let's say finding a black hole and orbiting around it a few times, just like Matthew McConaughey does in the film Interstellar. When I come back to Earth, say a year later, I could very well find that hundreds of years have gone by on Earth. So in a very real sense, I have time traveled into the future. It's not as though the future's out there waiting for me. It's just that I've moved into a different timeline and arrived in the future before everyone else. But what about the more interesting and paradoxical time traveling to the past? Well, this is the general relativistic equation for the space-time interval. You can easily show that this equation is completely symmetric under time reversal because it doesn't change when we reverse the direction of time, meaning it makes no difference if time flows forward or backwards. We say that general relativity is invariant under time reversal. There's no built-in direction to time. But general relativity suggests to us a way to actually travel backwards in time too. This is called a light cone. It's a really useful device in relativity theory. You see, I've plotted 3 axes here. I've got 2 space axes, x and y, and the vertical axis is time. Now, of course, space should really be 3-dimensional, but we're having to simplify it here just so that I can draw the diagram. Inside the light cone, this point here is the present moment. So you can imagine a moment in time where above it is the future and below it is the past. The point itself we call the here and now. All points above this point inside the cone are part of what is called the future light cone. So all points here represent events that can be influenced by this point. All points in the past light cone can influence this point. But any other points outside of the light cone can't be connected to it. They can't have been caused by it or cause it. Now, general relativity gives us a new picture of light cones because gravity in general relativity causes space-time itself to curve. As we know, general relativity says that gravity causes space-time to twist and bend. And with sufficient mass or energy, the top half of the cone, indicating the future, could begin to curve round. So that if you were to plot successive light cones, you'd find that they follow a curved path through space-time that bends back to the past. So traveling along this curved path, although you would feel yourself moving forward in time, you're able to return to a moment before you left. This is known as a closed timelike curve, or CTC. The physics is clear. Under extreme space-time distortion, you could, theoretically, travel back in time. But realistically, could these conditions ever exist? Because the amount of curvature of space-time needed to create a CTC would be huge, possibly at the event horizon of a spinning black hole, or maybe in a hypothetical universe developed by the mathematician Kurt Gödel, which required the entire universe to be spinning. Look, I'm not going to lie, this whole subject is very controversial. We simply don't know enough about these extreme distortions of space-time, these limits of what general relativity allows for, to really understand whether CTCs are actually possible. And many physicists, like Stephen Hawking, have found this whole line of argument disturbing and uncomfortable. In fact, Hawking was so convinced that the paradoxes of time travel couldn't be resolved and that CTCs were impossible, that our universe would simply not allow for time travel into the past. He came up with what he called the chronology protection conjecture, which suggests that the laws of nature just won't allow a CTC to form, and therefore time paradoxes can never happen. But there may be other ways to dodge the paradoxes too. In the mid-1980s, the Russian astrophysicist Igor Novikov came up with a neat idea. He suggested that if time travel to the past is to be possible, then the paradoxes would have to be avoided, with nature conspiring to make sure that the probability of any paradoxical situation occurring drops to zero. He claimed that only logically self-consistent solutions, that is, those that didn't lead to paradoxes, were allowed. And his idea is best expressed using this tiny pool table. So it goes something like this. Here is my pool table time machine. Now imagine a ball on the table is struck such that it goes into this pocket. Now this pocket is the entrance of the time machine, and the ball will pop out in the past somewhere on the table. Now it pops out, let's say, over here, and it travels along, knocking its younger self into the pocket. So it had to go into the pocket in order to reappear to lock itself into the pocket. This is the equivalent of my time-traveling scientist. His placing the instructions back in 2026 is the cause of his younger self building the time machine. Now, Igor Novikov suggested there would be whole areas of the table where the ball could reappear such that it would be able to knock itself into the pocket, and he called these consistent solutions. They were possible. There will be other regions of the table where the ball could reappear and not be able to knock itself into the pocket. Those were the inconsistent solutions. His consistent solutions he assigned some probability to. The inconsistent solutions had zero probability. So killing your grandfather had zero probability and therefore would never occur. So it would be impossible to leave the time machine instructions for yourself. Paradoxes just can't happen. Novikov ultimately put this in terms of a limit on free will. There are certain things you're just not allowed to do. Cleverly, he connected this with, say, not being able to walk through a brick wall or to jump over a tall building. There are just certain decisions you can't make. Recently, this idea has had a flurry of activity because of a new paper written by Dr Fabio Costa of Stockholm University and others. Their claim is that to eliminate the paradoxes, we need to think on a much grander scale. For them, it's not just about a single event and its consequences, but how the entire set of events behave globally, and then how that global framework can maintain self-consistency.
It is possible to have physically meaningful situations where it's not true anymore that there is a definite past and a definite future, and the causal influence goes from past to future, and still the laws of physics make perfect sense.
Costa's paper considers discrete slices of time on the CTC, and then defines the boundary conditions at their beginning and end. And then they ask, once these are set, how does the physics actually play out?
It's exactly equivalent to say, what is the situation just at the beginning of this small time that we're considering, and what is the condition just at the end of this small time, and in this limited region of space. So once these conditions are set, then the laws of physics should tell you what happens everywhere else, essentially.
They suggest that cause and effect now become just these boundary conditions. And then their maths shows that only combinations of boundary conditions that don't contradict survive.
It's not easy to get a good intuition without going through the whole math, in the sense, the best intuition is to understand that it looks like there should be a paradox, that I should be able to do something to break the systems. If we consider the billiard ball scenario, something is coming from my past, and I hit the ball in such a way that the ball cannot possibly come from the past in such a way that I've seen it. And the point is that this doesn't happen. So it looks like nature is smart enough to prevent such paradoxes.
So, they say, although you're free to choose, only choices that are globally self-consistent and make physical sense actually exist. But how does that change the grandfather paradox?
When we think about the story of the grandfather going back in time, we tend to focus, obviously, on just a few variables that make sense for the story. So the time travel, goes in the time machine, goes back. But there are, if we want to think about the whole physics, there are a lot of variables. When exactly the traveler comes back, who do they meet, what is the situation of their gun, is it loaded, not loaded, is it broken? And so essentially there are a lot of variables which we don't know, and that leave a lot of room for the paradox to sort of fix itself, to not appear. So, for example, it can be that the time traveler goes back in time, shoots a man, but this man turns out not to be his grandfather. Or maybe goes back, tries to shoot a man, and the gun doesn't work. Or there can be a lot of different resolutions which are consistent with this principle. Now, this is more like a writing, science fiction writing exercise more than a physics exercise. So physics at this level only tells you these resolutions are possible. And then how exactly it happens is exactly as all science fiction stories, physics cannot tell you exactly what the story is. You have to come up with the idea of the story. But physics can tell you what is possible and what is not possible.
So for Costa then, our time paradoxes disappear, not because they're logically inconsistent, but because they're physically not allowed. Of course, if we really want to get rid of the paradoxes of time travel, there is a way out, but it does require us to buy into yet another exotic, outlandish idea. And that is that our reality isn't the only one. There are parallel realities, parallel universes. Welcome to the many worlds interpretation of quantum mechanics. It boils down to a well-known quantum mechanics thought experiment called Schrödinger's cat. Imagine a cat in a box, and its fate, whether it lives or dies, depends on some random quantum event, like the decay of a radioactive atom. According to the traditional or Copenhagen interpretation of quantum mechanics, until it's observed or measured, the radioactive atom remains in what's called a superposition of undecayed and decayed states. And that measurement only takes place when the box is opened. Until then, the quantum state of the cat is tied to the radioactive atom and is both alive if the atom hasn't decayed and dead if it has decayed at the same time. When the box is opened, according to this traditional view, we trigger what's called the collapse of the quantum state. And suddenly, the atom has either definitely decayed or definitely not decayed, and the cat is either dead or alive. Many physicists, of course, didn't like this. They weren't in the majority, but some of them wanted to come up with alternative ways of explaining the mathematics. One of them was an American physicist by the name of Hugh Everett. In the 1950s, he came up with what we now call the many worlds interpretation. According to this interpretation, we can now reassess the Schrödinger cat problem in a novel way. It's beautifully simple because there's no baggage. All it says is that Schrödinger opens the box, and however many options there are, in this case, cat dead and cat alive, the universe branches into two realities. So in one universe, you open the box and the cat is dead. In the other universe, you open the box and the cat is alive. I have issues with it. It's very expensive on universes. There are lots and lots of universes, and possibly an infinite number of universes. There will be another version of me just because a particle on the other side of the universe decided to go left or right, and so the universe splits into two, one in which it goes left, another in which it goes right. There's also two versions of me as well. So it has its problems, but when it comes to helping us out to remove the paradoxes of time travel, then the many worlds interpretation is really neat. Take the grandfather paradox, for example. In the many worlds interpretation, by traveling back in time, you inevitably slide into a parallel reality in which you can kill your grandfather. All that then happens is that you're never born in that universe. But you, the time-traveling murderer, carry on living happily, well, unless you get caught by the authorities, because your grandfather was never murdered in your universe. So it's a big price to pay if we insist on time travel into the past being possible. I'm not convinced either way yet, but it's a fun way of getting out of some of these issues and paradoxes. There's been another new idea on the block which is definitely worth considering too. It comes from a young Italian physicist called Lorenzo Gavassino, based at the University of Cambridge. He's explored the quantum mechanics of CTCs and their effect on entropy.
So the thing that I imagine in the paper is, okay, what if I have a box perfectly sealed in such a way that there is no exchange of heat or anything, no irreversible process connecting the interior to the exterior of the box.
What we call an isolated system.
Right?
Yeah.
I play this spot experiment where I receive the box from the future, and then I build a time machine, and then I throw that box back in the past, and it becomes the box of the future, right? Now imagine that there was even someone alive inside this box, right? What would happen to whatever biological process or whatever thing or being closed inside the box that makes such a loop? Okay. And if you think about it, you are facing a situation that is similar to the Groundhog Day, you know, the movie, the Groundhog Day, where you have this person that experiences 24 hours and after those 24 hours, all their story is reset, right? Because they're back to the beginning. The next day is the same day they already lived, right? And then I asked the question, therefore, okay, what would happen in a realistic Groundhog Day scenario, which would correspond to the day of someone inside that box that makes the loop? And the reason why this is interesting is that then you can start to ask questions about thermodynamics.
Thermodynamics and entropy are very powerful concepts in physics because they give a direction or arrow to time. But they're also very slippery. Probably the most simple and common way of explaining entropy is to say it's a measure of the disorder of a system. The more tidy and neat a system is, the lower its entropy. And so this pile of papers here is nice and neat. I'd say it has lower entropy than when all the papers are spread out all over the desk. This is untidy, this is higher entropy, this is lower entropy. Technically, this is because there are more arrangements of messy papers that are indistinguishable to me than there are ways of stacking them tidily. And the famous second law of thermodynamics says that in a closed system, one that's not being interfered with or interacting with the outside world, entropy cannot go down. It can stay the same or it can increase. So these papers could gradually get messier, but they're not going to tidy themselves up. The second law of thermodynamics and the increase of entropy also gives us a direction to time in a way that no other laws of physics or dynamical equations of physics give us. It gives a point of time, an irreversibility to time from past to future. What Gavassino does that's really innovative is to link a quantum mechanical description of the start and end state of the time traveler through the CTC to their entropic journey. The idea is that as you travel around this closed time-like curve, you have to return back to exactly the same state that you started at, the initial state. He then links this to the idea of entropy, because entropy should always increase. But in this case, it must reach some maximum value and then start to decrease again so that it can return back to the initial state.
And what you discover is that the usual intuition that we have about the order of time, the fact that certain processes happen from past to future and not from future to past, they all break down. What happens is that our intuition about the behavior of physical systems is governed by this idea that there is an asymmetry between past and future. That is due to the second law of thermodynamics, the law of increasing entropy, which dictates this asymmetry between past and future. Well, inside this box, since the future and the past coincide, right, because midnight coincides with 00 time in one day, because past and future coincide, that very idea of an asymmetry between past and future breaks down, and so many strange things can happen. Yeah, if you imagine the quantity entropy, okay, and imagine that the entropy starts low, right? You start with a low entropy state, and then you let the system evolve. If eventually you need to go back to that original low entropy value, then at some point you must reach a maximum entropy point, right? After which entropy begins to decrease. And now the way that you can think about it is that after you reach the maximum entropy point, all the biological processes or the arrow of time that governs our head and our memory is reversed. So the way I like to think about it is, imagine that at t equals 0, the starting point of the box, the entropy is minimal. And let's say that at noon, okay, at 12, the entropy is maximal, okay? And then it will need to go back down because by the time you reach midnight, you need to go back to the original low value of entropy, right? So at the beginning, the entropy is low, it increases till the maximum at noon, and then it needs to go back to the original low entropy value, right? So if you follow that, then what is really happening is that there is a version of yourself that evolves from midnight to noon, and that experiences time from past to future, right, from midnight to noon, but there will also be a version of yourself that goes from midnight back to noon from the other direction, right? At noon, there are two versions of yourself that meet, one that travels from past to future and one that travels from future to past. And also at midnight, there are these same two versions that they also depart.
So in fact, the two versions of the time traveler, for both of them, that point of maximum entropy is somewhere in the middle of this curve is the future. So they
is
both,
the end, exactly.
So both of them are traveling from past to future and meeting at that maximum future point.
Exactly. So you look at where the entropy, so you have this curve, right? So you look at where the entropy minimum is, you look at where the entropy maximum is, and there are two parallel stories, in a sense, for whom the entropy minimum is the past and the entropy maximum is the future for both of them. But if then you follow the story in the loop, at some point it will look to you as if the person starts behaving as a time-reversed person, right? But from their perspective, they're just traveling from past to future. Right. It's just that their past and future, they start at the same point and they end at the same point, following opposite senses along the curve.
So this is different from the usual way I've always understood closed time-like curves, in the sense that if you're traveling along a closed time-like curve, I always think about it as going on a loop-the-loop on a roller coaster. You know, you're traveling forward all the time, but you arrive back at the point that you started. Yeah. And if you have if you're looking at a clock, your clock shows normal time. This is your proper time running forward along the curve as you go through curved space-time. Yeah. But it always runs forward all the way until you end back at the bottom of your loop. What you're saying is different. It suggests that it's running forward to this point. After that, to an external observer, it looks like time is starting to tick backwards to get you back to your initial condition. But in fact, what is really happening is there's the you moving around the other side of the clock. And the clock is also going normally. You look at the clock ticking by normally.
Then Gavassino gets speculative and starts to think about what decreasing entropy might actually look like, and what it might mean for his imaginary time traveler. Decay becomes recombination. Chaos becomes order. And in some sense, Gavassino claims, memory becomes erasure.
Now you can conceive that the younger person evolves and becomes the older person. And then since you have only two people, then something must happen. The older person dies and gets incinerated, and so it's no longer there, but you need to reform the younger person somehow, right? Something very strange will happen. But here is the very important thing to keep in mind, that if the box has the size of something like a room, and you look at the entropy inside that room, the total entropy inside that room, at some point it will begin to run backward, right? So if you are the younger guy, and you have close to you the older guy who tells you, I am the older version of you, you are not sure that you can trust them, because if this box is really making the loop, at some point, all the biological processes that govern memory are going to be erased, right? So you can't tell whether this person has made up fake memories that generated at the minimum entropy point, or if they really describe a continuous story. Because there is not a continuously increasing entropy on the basis of which you can justify the memory of this person, right? That person has a memory, but you don't know if you can trust it, because memories to be accurate must rely on the second law, and you know that the second law will break at some point, so you don't know if you can trust it, right?
So, with the second law violated and memory corrupted, Gavassino claims to have escaped the paradoxes by suggesting that the time traveler is just not the same person as his grandfather. It's definitely a bold and provocative new paper, and I quite like it.
It's what we do, particularly as theoretical physicists, in testing our current understanding of the laws of nature, testing our equations and theories to breaking point to see if they work, and whether it's closed time-like curves, whether it's wormholes or whatever, general relativity is still our best theory of the nature of time. So we want to push it to the limit.
Exactly.
I think that's what you've done very nicely in this paper. Let's see how far we can push it and see if I can break it. Surprising results.
Without introducing any new assumptions that are not generically agreed upon. That was the rule of the game.
Lorenzo, thank you very much indeed. But I can't help feeling that this, along with all the other ideas we've been talking about, miss one point. If time travel is technically possible, and one day it does eventually get invented, where are all the time travelers? Well, there are several explanations and answers to this question. The most sensible one is that if a time machine is ever invented, then we can only ever use it to travel back to the moment it's switched on. All times before that moment are gone. They're lost to us. So if we invent a time machine in 100 years, for example, then 200 years from now, we could use it to travel back 100 years. But you could never use it to travel back to today. There are two other possibilities that answer this question. There are no time travelers from the future among us today because no one wants to come back to 2026. Maybe they're waiting for us to sort out our problems and make the world a nicer place to visit before they set up their package tour holidays into the past. Finally, it may be that time travelers from the future are walking among us today. They're just keeping a low profile. In fact, some of you might even be out there now. If so, please leave a comment.